Okay, so in this video, we're just basically gonna focus on we're gonna look at some problems in the 2022 paper for the MATM 1534. Okay, so here we have a to the power ln a equals 3 ln 3. It's one of those questions in section B there. So if we look at this question, we want to solve for a. How do we solve for a? Notice that here you have a raised to ln a. So what you can do is that you can take ln on both sides. So what happens if we take ln on both sides? If we take ln on both sides, then we basically have something like this. You know the rules for logarithms. Then you basically have if you have ln of a to the power of b, then you're basically going to say that's going to be b ln a. So we can just do that, take this on the outside, and so it's basically just going to be ln a ln a. This is the ln a that's there, and you end up with basically this, which is this ln a right here. And so if we look on the left side, and on the right side, we're basically going to remain with ln 3, right? So we have something like that. And notice that if you have ln a by ln a, that's just going to basically be ln a squared. And so here we basically have ln 3, that's just going to be ln 3 squared. And so you can basically just equate to 0. So you basically have ln a squared minus ln 3 squared. That's just going to technically give us 0 if you take everything on one side. And so when you have this, notice that you have a square term minus another square term. And you're familiar with the difference between two squares, so that's basically just going to be it. So then you factorize the difference between two squares. Remember, a squared minus b squared, that's just technically going to be equals to a plus b, a minus b. Something like this, multiplied by a minus b. So you basically have something like that. And so when you have this, then that means that you can say you have ln a plus ln 3 multiplied by ln a minus ln 3. So this will technically give us 0. And so when you have this, then that means that ln a will be equals to minus ln 3 for the first bracket there. And then for the other bracket, you technically have ln a equals ln 3. So you can have two solutions like that. And so if ln a equals minus ln 3, that technically means you can take the negative. This is the same as you're saying negative 1. You can take the negative back in and it becomes a power. So that will just technically going to be ln 3 to the power of minus 1. And so this side you just have ln a equals ln 3. And this side you have ln a equals ln of 3 to the power minus 1. And we know ln 3 to the power minus 1 is the same as 1 over 3 to the 1. You just technically make it be a denominator and you raise to the positive power. Whenever you have a negative power, then it's 1 over that positive power, that term raised to that positive power. So this is just technically going to be ln a equals ln of 1 over 3. And on the side you just have ln a is ln 3. So that means that a ln, so you can raise both sides. You can have both sides being e to the power that. So that technically means that you can do the same here and say you have e to the power ln a. This will be equals to e to the power ln 3. And you know when you compose a function into its inverse, you're technically going to get the value that's there. I mean, a function composed at its inverse at x will technically be x. But since this one is composed at 1 over 3, then that's just going to be 1 over 3. And so this one is composed at 3, so that's just going to give us 3. So you have two solutions to that problem. So, okay, so now let's look at this one right here. So we have the limit as x goes to infinity of e to the power 5 over x. And the nice thing about this is that when you have like a composition of functions, let's say maybe now, let's say you're evaluating the limit when x goes to something of f composed at g at x. Notice that here, when you evaluate f at g at x, that x is dependent on that variable that we're taking the limit of. So that means that now we can basically distribute the limit on sides. It's actually the properties of limits. So then you can have, this will be f evaluated at the limit when, okay, let me just rewrite that. This will be f evaluated at the limit when x goes to a of g of x. Because technically we're evaluating f at g, right? So if we evaluate the limit of g, then we can technically get the limit as x goes to a of f at g. And so now, here if you check, you can say maybe your function, your outside function was e to the x, that will be f. And then it will be composed at g, which is just 5 over x. And so, then that technically means that we can actually like take that limit up there into the inside function. So then that technically implies that we actually have e to the power the limit as x goes to infinity of 5 over x. And so when we have this, then you know what happens when you actually divide by a large denominator. As x goes to infinity, the larger the denominator, the actual smaller the quotient will be. And so that will technically approach 0. So you end up having to have e to the power of 0, and any number aside 0 to the power of 0 is technically going to give us 1. So that's what we have. And so that will be the solution to that one. So here if we look at this, we have y equals d over dx of ln cot x. And what we want to find is we want to find dy dx. So basically if y equals that, so that technically means that dy dx will just be basically be d over dx of y, and y y is just this. Y is just d over dx of that. This is basically just y. So then that means that we are taking d over dx of ln of cot x. Ln of cot x. So we're basically having something like this. And so now if you focus here, we'll end up having to have d squared over dx squared. So that just means just take the second derivative of that, of ln cot x. And so that's what we have. We have d squared over dx squared of ln cot x. And so if we want to take the derivative of that, second derivative of that, we can actually simplify this. We know that cot x is basically going to be cos of sine. So we have ln cos x minus ln sine x. So that's technically what we have. And so now we want to take the derivative of that. Notice that the derivative, if you take the first derivative of that, so that means we'll have d over dx of, take the derivative of that, the derivative of cos is negative sine, so we end up having to have minus sine x over cos x, which is just going to be tan x. And then if you take the derivative of this, it's just going to be cos x, and then you divide by sine x. Remember, the derivative of ln is the derivative of what's inside over what's inside. So that's the derivative of cos, which is sine, divided by what was inside, which is just cosine. And so then from here, we're basically just taking d over dx of this. And so we have d over dx of negative tan x minus cot x. But for me, let me just leave that as it is right now. And so that means that now we're basically going to end up having d over dx of tan x, which is just going to be secant square x. And don't forget, we still have this negative right there. So we have minus secant square x. And so if you derive this, you can use the quotient rule. So then you're basically going to have the derivative of cos, which is negative sine. Multiply that by the denominator, then you have sine square. And then minus... remember, with the quotient rule, you divide by the square of the denominator. So then here you'll have cos x multiplied by the derivative of this one, which is just going to be cos x. So you'll end up subtracting cos square x. And we know that we have negative sine square minus cos square. You can factor out a negative, and then you end up having to have sine square plus cos square, which is just 1. And because of a negative, then that's just going to become minus 1. But notice that we have another negative right here, so that's just going to be positive 1. So we end up having to have 1 over sine square x. So we have minus secant square x plus 1 over sine square x. And we know that 1 over sine square x, secant square x, we know that 1 over sine is technically cosecant. So we are basically adding cosecant square x. So that's basically what we have right here. But you can further start with the positive term and say you have cosecant square x minus secant square x. So that will technically be it. So yeah, that's that. Okay, so now we basically have this function. So what we want is we want to find where's this function increasing or decreasing, and we also want to find the local minimum and maximum of this function, and we want to test whether which interval is this concave up or concave down. So, and also the inflection point of that function, if we may. And so if we look at this function here, in order to find where this function is increasing or decreasing, we basically need the first derivative. So if we check the first derivative, and then we just basically have 6x squared minus 18x plus 12. That will be the first derivative of that function. And so if we basically have this, we basically need to see where is this positive or negative. So it's easier to just find the critical numbers of that. 6x squared minus 18x plus 12 equate it to 0, so you can basically solve for the critical numbers of that. So then notice that you can basically divide everything by 6. So then we have 3, and this one will basically give us 2. So what we want is two numbers that multiply to 2, add or subtract to 3. And those numbers will basically be 2 and 1. And so we basically have 2 and we can have 1 there. So you have xx. The bigger number will take the middle side, and so you have a negative. Notice that the constant here is positive, so you only need to you need 2 negative numbers that will multiply to a positive. So those are the factors of that. And so then we basically end up with x equals 1 and x equals 2. Those are our critical numbers. This is where the derivative is equals to 0. And so so now we have 1 and 2. That's where the slope is 0. And then if we plug in here, this is similar to the first derivative. I didn't change any signs or some sort, and I only divided by a positive number, so I can basically use this. So then if I plug in a number less than 1, for example 0, if you plug in 0, you have minus 1 multiplied by minus 2, which is going to be positive, so that's where the slope is positive. And if you plug in a number between 1 and 2, 1.5, so 1.5 minus 1, that's 0.5, which is positive, and then 1.5 minus 2, it's going to be negative 0.5, so you have positive by negative, that's going to give us negative. Plug in numbers larger than 2, 3, then we have 3 minus 1, that's positive, and 3 minus 2, that's positive. Positive by positive is positive. And so we basically see that for increasing, this function is increasing if for all numbers less than 1, and all numbers larger than 2. So how do we put that in interval form? So we know that x will be a set of all negative numbers to 0 and up to 1. So every number less than 1. So, and we also have that interval proceeds and starts from 2. And notice that 1 and 2 are excluded because at 1 and 2 the derivative is 0. It's not increasing or decreasing, it's just stationary. So, and that means that we have that 2 to infinity. That's where this function is increasing. And so for decreasing interval, that means we technically have x being between 1 and 2. So that's where it's decreasing. That's where this function is decreasing. So, okay, we know where the function is increasing or decreasing. So now that we have the increasing and decreasing interval, how do we get the local minimum and local max? Local minimum and local maximum. Okay, so notice that here this graph increases to a peak, and then it goes down, it slopes downward. So that means that here we'll have a local maximum. When the gradient goes from being positive to negative, you basically have a local maximum. So we expect a maximum to have a coordinate of 1. So that means to the original function you plug 1 there. So you have 2 minus 9, that's going to be minus 7. Minus 7 minus 3, that's going to be minus 10. Plus 12, that's going to be 2. So you have 1, 2. That will be the coordinate of that. And so notice that here it goes from decreasing to positive. It goes lower and lower and lower, and at 2 then it starts to shoot up. So that means that at 2 you expect a local minimum. So then the x coordinate would be 2, so you can plug 2 there and see what happens. So we have 2 cubed, that's 8, by 2, that's 16. 16 minus 3, that's going to be 13. And 13 plus 2 here, that's going to be 24. 13 plus 24, that's going to be 37, right? 4 plus 3, that's 7. Yeah, that's going to be 37. So when we have 37, 2 by 2 right there, that's 4. 4 by minus 9, that's going to be minus 36. So you have minus 36 plus 37, that's going to be 1. So we have something like this. So this will be our local minimum and local maximum at that point. So then where do we check? How do we check concavity of this? So notice that here, for concavity, we basically need the second derivative. Since we already have a first derivative, then we can easily take the second derivative of that and say, okay, we'll basically have 6x squared, the derivative of 6x squared, that's going to be 12x. The derivative of negative 18, that's going to be minus negative 18x, that's going to be negative 18. And the derivative of 12, that's 0. So in order to check for concavity, then we know since our second derivative is this 12x minus 18, we equate to 0, and that way we can get the x coordinate for the inflection point. So basically that get 12x equals 18. Divide everything by 6, then we have 4x. Right? We have 2x. 12 divided by 6 is 2, and then this will basically be 3, and so x will technically be 3 over 2. So that's the x coordinate for the inflection point. And so we have that inflection point there. And so since this is the second derivative, if you plug in numbers less than 3 over 2, for example, you can plug in 0. You have negative 18, so it's negative. And if you plug in numbers larger than 3 over 2, for example, you can plug in 2. 2 by 12, that's 24, which is greater than 18, so we expect a positive here. So then you can basically tell that for concave upwards, you technically have all x values larger than 3 over 2. That's where it will be concave upwards. And for concave downwards, we expect all values less than 3 over 2, where the second derivative is negative. And so then that technically means that we have something like that. So from all the way, it's from minus infinity to 3 over 2. So that's where the thing will be concave downwards. And in order to find the sketch of this function here, you can just basically start with the intercept and start with the properties that we found here. We have found the local minimum and maximum. And so we can easily be able to sketch that. So basically this is something that we have. Okay, so notice that we have a local minimum at 2, and we have a local maximum at 1, at x equals 1. These are the x coordinates. And if x is 2, y is 1. So that's that. And if x is 1, y is 2, and that's that. Notice that the intercept will be minus 3 here. And so then we basically have something like that. That will be the sketch of f. So f defined by this function right here will basically look something like this. Don't forget to label your coordinate, your axis. Don't forget to label your axis. So that's how you'll be solving such type of questions.